Hello everyone and welcome to this model on content exchange. In this model, we're going to talk about Bitswap, which is the main content exchange protocol in IPFS. And we're going to describe also GraphSync, which is an alternative way of exchanging content one-to-one in the IPFS network. To wrap it up, we're going to make a brief comparison between Bitswap and GraphSync to understand the similarities and differences. But before we start explaining Bitswap and GraphSync, let's have a quick detour to refresh how content is represented in the IPFS network. Content is usually chunked in blocks in the IPFS network. So when we have a file, we chunk it into different blocks. Blocks are abstractions of serialized information, so that if we aggregate all of the information included in the blocks that comprise a file, we are able to recover the file. Blocks are uniquely identified by a content identifier or a CID, and this content identifier is inferred from the hash of the information included in that block. And blocks may be linked one to another through a DAG structure, so that if, for instance, we have a file and we have the different blocks of a file, we can have a root CID with all of the links that link to the blocks that represent the information of the file. And also with this DAG structure, we can represent more complex data structures, as for instance, directories, where we can have a parent directory, different directories through links, and then the links to the blocks of the files inside the directory, and so on. And these DAG structures can also be represented using what we call IPLD graphs. And IPLD is just a standard of representing linked data in a decentralized way. So with this quick detour about content in IPFS, let's jump into explaining how Bitswap works. Bitswap uses a modular and implements a modular architecture. In the end, Bitswap is a message-oriented protocol to exchange blocks in a peer-to-peer network. Bitswap is the main content exchange protocol in IPFS, but it could be used in any other network or any other application. The first thing the first model in the Bitswap architecture is the Bitswap protocol interface that exposes two main operations to the outside, which are the get operation and the put operation. With the get operation, what we're saying Bitswap is that we want to find a block for a specific CID. And with the put operation, what we are just letting know Bitswap is that we are storing certain block and that we can start providing it to other nodes and other peers in the network. Below this Bitswap protocol interface, we have the following models. We have a connection manager because Bitswap leverages the transport protocol and the network interface that may be in place in the environment or the node where it operates. So this connection manager in the end communicates with the network interface in order to orchestrate the interaction with other peers and the exchange of messages with other peers. So in the case of IPFS, the connection manager talks to a lead peer-to-peer node, which is the one in charge of the transport abstraction and the interaction with other peers in the network. Also, this connection manager leverages currently established connections in the peer. We'll see in a moment how. Then we have the ledger and the block store. In the ledger, what the Bitswap node does is to track the interest for certain blocks from other peers in the network. So every time that we receive a request for a CID from other peer, we track this interest in the ledger. And for each peer, we will have what we call the wantlist. That the wantlist in the end is just a list of the CIDs that other peers may be asking for. In this way, whenever we receive the block for a CID, which other blocks in the network, other peers in the network may be looking for, we can send it to them right away because the ledger knows that the interest from other peers, it communicates with the block store and it's able to send directly the block. And finally, we have the session manager. Whenever we start new discoveries and downloads of content with a Bitswap node, we start a new session. So sessions in the end orchestrate parallel streams of discovery and fetch of content. The session manager orchestrates all of the active sessions that there may be in a Bitswap node. So when we try to find content for a specific CID, we start a new session, and in the session we keep track of information that is useful to find the content and contact the peers that may be storing the content in the network. And the session manager interacts with the content routing interface in order to get information about providers and about where content may be stored in the network. So this content routing interface in the case of IPFS, interacts with the DHT in order to find providers for the content, but it may interact with any other kind of providing subsystem, like a network database, DNS, or any other content routing implementation that may be in place in the network. And to understand how Bitswap operates, we're gonna use the example of fetching content from the IPFS network. Because whenever we try to find content in the IPFS network, the first thing that our IPFS client does is to check if it has any of the blocks for that content in its block store. And if this is not the case, it starts and it triggers a new Bitswap session to start fetching all of the blocks for the content that the IPFS client is looking for. We'll see that as Bitswap is a message-oriented protocol, we will have 6 different messages in Bitswap, 3 request messages and 3 response messages. First, we have a one-half message that may be responded with a half or a don't have. And what we're doing when we're sending this request is asking if any of the blocks to whom I'm sending the request is storing that content. If it is storing the content, it will send a half response, and if not, it will send a don't have. Then we have the one block request. With the one block request, what we are requesting is information. We're requesting is explicitly the block for the CID that we include in that request. So if we send to appear a one block and they are storing the block, they will answer directly with that block. And if they don't have the block, they will answer with a don't have. And finally, we have a special request that is the cancel message. That is to let other nodes know, other peers know that I'm not interested in a specific CID anymore, because either I'm not interested in that content anymore, or I found that block by other ways or through other peers. Before we start with a specific way in which Bitswap operates, we need to make another quick detour to understand common retrieval patterns in the IPFS network, because when we try to find content in the IPFS network, we can do so in different ways. We can download a full directory of a full file, in which case what we do is to download all of the DAG structure and all of the blocks for a DAG structure. This is the case that we see in the left, where when we try to find a file, what Bitswap will have to do is to first download the root CID that has all of the links for the rest of, for the next level of the DAG structure. It would get that root CID, inspect the links, and request the blocks for the next level of the DAG structure. And if there are following levels, it would do the same, like take the links of the next of this level of the DAG structure and then go down to get all of the blocks of the next level until it traverses the full DAG structures. This is what Bitswap usually does when it's trying to fetch files or trying to fetch full directories or full datasets. But we have other common retrieval pattern, which is the one that we use when we want to render a website or an asset with our browser that is stored in the IPFS network. In this case, instead of looking for the root CID for all of the DAG structure that we want to download, what we do is get or fetch the content through a path. So instead of going to the specific root CID and get all the DAG structure, in this case, we will send Bitswap information about a path, and Bitswap would have to traverse that path until it gets to the file that we want to download. So in this case, if we are trying to download or render through our browser the file web/page/docs.html, what Bitswap would do is to first get the root CID, inspect the links, and only get information about the link that we're interested in this case, page. So it would go to the next level, and in the next level, it would get the block for page, inspect the links, go to the one of doc.html, and then inspect the links and request all of the blocks for that doc.html. So we see that in this case, instead of downloading every block in each level of the DAG structure, we are only traversing the DAG structure until we get to the file that we want to download. And this is the behavior that Bitswap will do and the request pattern that Bitswap will follow in order to traverse the DAG structure and get the content the IPFS client may be interested in. So as I've said, the moment an IPFS client starts trying to find content in the network, what it does is to trigger a new session in Bitswap. And new sessions, the first thing they do is to leverage the currently established connections to broadcast a want message a want have message to all of the neighbors. So what we would do is to check all of the established connections and send a want have to all our neighbors. And in parallel, Bitswap will start a DHT work in order to find potential providers for the content. So in the case that we're not able to find the content in any of our neighbors, we can start finding providers through the DHT. So we send this broadcast, this one half broadcast, and we will start getting half responses from the different peers. In this case, we see that we've received a half response from 2 of our neighbors, and we were able to find a provider through the DHT work for the CID that we're looking for. And this broadcast is done only for the root CID, because we want to find the root CID of the content we're trying to look for, so that we can get the links for the following levels and we can start fetching the following levels in the DAG structure. So this is how the RTT works for and the back and forth of message work for the discovery of these and the broadcast of this root CID. We send a one half to all our neighbors, and the moment we receive a half message from one of our neighbors, we can't send a want block for that CID because we know that he's storing that content, so that we can get the block back, the root CID, and we can start inspecting the links for the following levels of the DAG structure. But in the meantime, we may start receiving half messages from other peers and other of the neighbors to which I sent this request. And we're not discarding these requests, because we're going to use them to add these peers to the session. Because if these peers are storing the root CID for the content, they may potentially be storing the rest of the levels of the content. So in order to avoid having to interact with all of our neighbors and providers for the following discovery of the blocks of the level of the DAG structure, what we do is to add all the peers that have responded successfully to the discovery of the root CID to this broadcast stage. We add them to the session, so that from now on, instead of talking to everyone, we're only going to talk to the ones that successfully responded to this first request. So we broadcast the one half, we get the half, we get halves from different files, and we end up getting the block from one of the neighbors that were storing it. We get this block CID, we inspect the links, and we start fetching all of the blocks for the following levels until we traverse the DAG structure and we get all of the content that we're interested in. So, and this is what we're seeing here. Once we get the root CID and we inspect the links, we can start sending requests for the rest of the blocks. And instead of like contacting everyone as we did in the broadcast stage, now we are only contacting the peers that are inside the session. So we will send a different pattern of block messages and of one blocks and one halves, and go back and forth in this way until we traverse the full DAG structure and the full tree that we've seen before. So according to here, we're sending, like for instance, from peer A, we're sending to peer B 3 want block requests and one halves for the rest of the blocks of the CIDs of the blocks of the next level. And in this way, we can send non-overlapping patterns that the peers in the session can answer with the block, with halves, or we don't halves until we get all of the blocks of the next level. And we do this back and forth continuously until we get all of the blocks of the content. The reason why we see this in this way is because Bitswap messages can include more than one CID. So the Bitswap message in the end is an envelope in which we can include more than one half, one block, or different requests for peers. So here we're having the same Bitswap envelope where we're sending this pattern of requests to the different peers in the session. And another thing that is worth noting is that if at one point we have a peer, like for instance, we could have peer B continuously sending unsuccessful responses with don't haves for the content we're looking for, it would mean that for the DAG structure that we're looking for, it doesn't have the lower levels anymore. So we will remove it from the session. And once we've remove it from the session, we don't send subsequent requests anymore. And if at one point we remove, because any of the peers in the session has the block that we're looking for, and we remove all of the peers in the session, we have to start a new broadcast stage in which we do in parallel a DHT walk and again a broadcast to the neighbors in order to populate again the session with potential peers that may be storing the content. From now, instead of going from the root CID, we start from the block that we were when we run out of peers in the session. And this is the view from the peer that is requesting content, but then for the peer from the peer that is providing content, what we see is the following. We may be receiving once request for different CIDs, and every time that we receive one of these requests, in this case, the receiving peer will update the ledger and the want list for that peer. So we see that here peer A is sending requests to peer B, and peer B is updating the ledger according to the CIDs that are being requested by peer A. If at one point peer B receives the block for one of the CIDs that peer A is interested in, it will right away send it to peer A and remove that CID from its ledger, because it means that, as I've sent the block, it means that A already has that block and is not interested anymore in it. And also, I said that we had a special request message, that is the cancel message, that is used because we are sending a lot of requests to all of the peers in our session. And in order to avoid receiving duplicate blocks, if peers end up having finding the block, what we do is that every time that here peer A is sending requests for CID1 and CID2, we may receive at one point from any of the other peers of the session the block. What we do is that the moment peer A receives a block for a CID, it is looking for, it sends a cancel message for that CID to all of the peers in the session to let them know that they are that it already has the block. So in this case, we saw that peer A is sending requests to peer B is updating the ledger. At one point, peer A receives the block, and to notify all of the peers in the session that it has found the block and is not interested in it anymore, so it can be removed, that CID, from the ledger want list of the rest of the peers in the session, we send a cancel message to all of them. And this is what we're seeing in this figure. So this is briefly how Bitswap works. Let's jump now to GraphSync, to describing GraphSync, which is an alternative way in which we can exchange content in the IPFS network. And GraphSync is a request response protocol to synchronize graphs across peers. We use IPLD selectors to request the blocks of the graph to be exchanged. So in this case, instead of asking block per block the blocks that we wanted to download from other peers, we use IPLD selectors in order to choose the specific blocks, to implicitly choose the blocks from the graph that we want to download. So in this case, we can see some examples of IPLD selectors here in the top right, where we see that we can select single blocks using a selector like this one, where we select the CID for that block. We can use path selection, where we want to select a specific path and all the blocks for a specific path in the DAG structure, like the one we see in green, and we can even select full branches of DAG structure. So we have a lot of combination of IPLD selectors that we can use to find, to request the download of content from the network. And as I've already advanced at the beginning of the presentation, IPLD in the end is a decentralized data structure to represent these linked data and these DAG structures. And with these selectors, what we do is identify a subset of nodes, a subset of blocks that we want to download from content that is stored in other networks. One of the limitations that GraphSync currently have is that it doesn't have content. In Bitswap, we saw that we use a gossip-based approach in order to perform content discovery, and in parallel, we leverage the content routing interface to find providers for the content. This is not the case in GraphSync, and as we use a request response approach, in the request, we need to specify the peer from which we want to sync or download the DAG structure. So we would have to be sure that the peer we're contacting already has the content and already has the content in order to be able to download the content. If not, we will just, the other node will say that it doesn't have the content, and that's it. That's why we say that it's a one-to-one exchange, of content in IPFS because there's not content routing and we only have the exchange of blocks. And how it works is really simple. What we do is to send a single CID plus some metadata to the other peer to let them know the specific selector that we want to download, the blocks, and in what extent. And if the other node has the content, it would directly open a stream and send all of the blocks right away without any additional request to me. So I would send a single CID with this selector and the metadata. The other node would be able to understand like what is the structure of the DAG structure and the number of blocks that needs to be sent. It will open a stream and send the blocks right away. And GraphSync is also used in Filecoin, for instance. It can be used in other systems at Bitswap, and is used in Filecoin to exchange blockchain information and synchronize user data between different peers in the Filecoin network. And to wrap up, let's do a quick comparison of GraphSync and Bitswap. We saw that Bitswap is a message-oriented protocol, while GraphSync was a request-response protocol. In Bitswap, we requested content block per block. We had a back and forth with the different blocks and different peers in order to fetch all of the blocks of the content and discover the next level and the following blocks that needed to be requested. And in the case of GraphSync, the content exchange is performed through a stream where we just send the selector of the implicit blocks that I want to download, open a stream and receive the blocks right away. The request patterns for the content to download the content also was different, because while in Bitswap we used a CID path in order to download the content and specify the blocks of content in the DAG structure that wanted to be downloaded. So we had to explicitly say the blocks that we wanted to download. In GraphSync, we can do more complex queries where we can send an IPLD selector and express the different structures or different subgraphs in an IPLD graph or a DAG structure that I want to download. The way in which both of them work implies that while Bitswap can leverage multipath download because we can send requests to non-overlapping requests to different peers, this is not the case for GraphSync, because in GraphSync we need to know the peer that is storing that content. We open a stream and we do that interaction with it right away. So we send the request and we receive the response. So the kind of use cases for which both are used are some of them similar and some of them really different, because both are used for file sharing and download. But while Bitswap is used for files and data structures where we don't know where it may be stored in the network, for GraphSync, we need to know the peer, or at least a peer that is storing the content we're interested in. And that's why it's used for things like a blockchain sync or large data set sync, where we are all sharing the same data and we know that peers that potentially may have it, so that we can start a request with them. This is not the case for Bitswap, that can be used in environments where we don't know where the content is stored, because it does this back and forth between different peers in order to find the content and download the content. And also it is embedded with content routing capabilities in it, so it can interact with a content routing interface to find providers for the content and even accelerate the behavior of content routing and the content routing and providing subsystems that are in place in the network. And this is all for content exchange in IPFS. I hope you enjoyed this model, and feedback or any comment that you may have is more than welcome. Thank you.